What if a fragment from another star system suddenly began to glow, as if something inside it had awakened? What if, out there in the silent deep, an object that should have been cold and lifeless instead began to grow brighter, faster than any comet ever recorded? And what if that light did not fade but pulsed, as if responding to our sun? In the late months of 2025, astronomers across Earth in orbit watched a quiet traveler named 3I Atlas do the unthinkable. Within days, its luminosity surged, its body seemed to swell, and its spectral lines bent into forms that refused explanation. No ordinary comet should behave this way. Telescopes turned, data streamed, equations collapsed beneath what they saw. For the third time in human history, an interstellar object had entered our skies. But this one was alive with change, radiating a mystery powerful enough to challenge the physics that birthed it. The cosmos had whispered once again. Something in the dark had spoken through light. This is the story of 3I Atlas, its awakening, its impossible growth, and the unanswered question it leaves behind. What truly is shining at the edge of our understanding? If the unknown moves you, subscribe. It helps bring you closer to the wonders waiting beyond. In the first week of July 2025, a faint object appeared in a patch of sky that telescopes had scanned countless times before. It looked ordinary, a moving point of light drifting against the static field of background stars. Its initial measurements placed it between Jupiter and Saturn's orbits, moving sunward at nearly 70 kilometers per second. For most survey operators, that was fast but not impossible. Many comets fall inward from the Oort cloud with tremendous speed. Yet the Atlas system flagged something different. The path did not close. The orbit was open, hyperbolic, and steep. Its curve did not bend toward return. It bent toward escape. At first, astronomers believed it might be a miscalculation, a software artifact. Orbital solutions often fluctuate during early detection, but additional observations from Chile, Hawaii, and the Canary Islands confirmed the same conclusion. The object was not bound to the sun. It had come from beyond and would one day leave the same way. Within days, the Minor Planet Center gave it a new identity: 3I Atlas, the third confirmed interstellar visitor in human history. For the teams that had followed 1 Oumuamua in 2017 and 2 Borisov in 2019, this was both familiar and thrilling. Interstellar visitors are snapshots from other star systems, messengers carrying chemical fingerprints from alien suns. But what set 3I Atlas apart was not only its arrival, it was its behavior. During those early weeks before the brightening began, astronomers treated 3I as a quiet opportunity for data. Its brightness placed it well within reach of mid-sized observatories. Spectrographs gathered its light, and software broke that light into spectra, the chemical barcode of the object's surface and gases. The readings were strange. Ratios of carbon isotopes did not match known solar system values. The water ice lines were offset, and there were traces of nickel and iron that suggested a metallized crust beneath a layer of volatile material. Some researchers proposed that 3I Atlas might have formed in a region closer to its parent star, where heavy metals condense. Others noted that its internal balance of oxygen and carbon implied formation in a carbon-rich system, perhaps one that had long since burned out or been torn apart by gravitational interactions. The isotope ratios hinted that this fragment was billions of years older than Earth. With each analysis came a picture of unimaginable travel. 3I Atlas could have been expelled from its home system by a passing giant planet, flung outward through interstellar space. Over hundreds of millions of years it would have passed through nebular dust and interstellar gas, slowly eroded by cosmic radiation. Micrometeorite impacts would have scarred its surface, each one leaving traces of alien chemistry. For billions of years it would have been little more than a frozen, tumbling relic, darkened by carbon soot, its internal ices preserved in the cold between stars. By mid-August 2025, the orbital solution was clear. The trajectory entered the solar system at an inclination steep enough to take it above the ecliptic plane, diving inward toward perihelion. The velocity relative to the Sun exceeded 45 kilometers per second, too high for capture. Once it passed perihelion, it would never return. The total duration of visibility would be measured in months. In scientific circles, the mood was cautiously celebratory. Each interstellar object offers a rare data point for planetary formation models. Oumuamua had defied classification, neither comet nor asteroid, lacking both tail and gas. 2I Borisov behaved more like a traditional comet, venting volatiles as it approached the Sun. 3I Atlas seemed to occupy a middle ground, a body with both solid metallic properties and faint outgassing behavior. It was as if the universe had sent 3 examples of one puzzle, each piece slightly different. The early images showed a nucleus roughly 1 to 2 kilometers across, surrounded by a faint diffuse coma, the gaseous halo of sublimating ice. Nothing remarkable appeared, yet the precision of its motion told a story of exact balance. The object's rotation remained steady. Its angular momentum did not wobble or precess. This stability suggested that it was dense, perhaps with a rigid core. That finding alone challenged early assumptions. Most small comets spin irregularly, their jets pushing them into chaotic tumbling. 3I Atlas moved with measured calm, as if its forces were internally regulated. By September, large instruments joined the study. The James Webb Space Telescope, positioned beyond Earth's atmosphere, measured the thermal signature of 3I's surface. Its infrared readings indicated higher reflectivity than expected, possibly a crust of metal-rich dust or frozen carbon compounds that scattered sunlight more efficiently. Meanwhile, ground-based radar attempted to resolve its shape, though distance and speed made the results uncertain. The more astronomers looked, the older it appeared. Calculations of galactic motion traced its incoming vector backward across tens of thousands of light years. Models suggested origin within the thick disk of the Milky Way, where stars are older and metal content lower. Some simulations placed its birth in a system that formed before the Sun, a star now long dead or absorbed by stellar evolution. Atlas, in this view, would be an orphan, traveling between generations of stars. Each interstellar visitor rewrites a part of cosmic history. When 1I Oumuamua was first detected, it forced astronomers to confront how much material is exchanged between star systems. It implied that planetary formation throws vast quantities of debris into interstellar space. By the time 3I Atlas arrived, scientists had begun to realize that the galaxy may be filled with such wanderers, passing unseen through the dark. The solar system, it seems, is not isolated but immersed in a slow, invisible traffic of ancient matter. For several weeks, 3I Atlas remained unremarkable. Its light curve held steady. Observatories logged routine measurements and computer models predicted its likely appearance near perihelion. Then subtle anomalies crept into the data. The brightness did not follow the expected curve for a body approaching the Sun. Instead of rising smoothly, it fluctuated, brief dimming followed by rapid surges. The comet's density appeared to change unevenly, as though something within the nucleus was shifting. At the time, these fluctuations drew little attention. Photometric noise, instrumental drift, or local seeing conditions could explain small variations. Yet in retrospect, those first irregularities marked the beginning of what would become one of the strangest light curves ever recorded. For now, in the early stage of its journey, 3I Atlas represented a textbook case study in interstellar capture dynamics. The focus was on motion and chemistry, not on anomalies. The excitement lay in its origin. The prospect of analyzing matter formed around another sun carried immense value. Every molecule ejected from its surface was a sample from beyond the solar system. In laboratories, astrochemists awaited the composition spectra, the lines that would reveal the balance of elements, the ratio of deuterium to hydrogen, the presence of noble gases. When those numbers arrived, they were extraordinary. The deuterium fraction was unusually high, implying condensation at extremely low temperatures, perhaps near absolute zero. Such conditions exist only in the outermost reaches of protoplanetary disks or in the interstellar medium itself. The oxygen lines showed depletion relative to solar system comets, suggesting chemical evolution under cosmic ray bombardment over immense time spans. The isotope data pointed toward an age of up to 12 billion years, older than Earth, older than the Sun, possibly older than our spiral arm of the Milky Way in its current configuration. 3I Atlas was, in a literal sense, a fossil from a previous cosmic era. For astronomers accustomed to working within the temporal confines of their instruments, these scales were staggering. Every observation was a message from a time before planets like ours existed. When light from the object reached telescope sensors, it carried the record of countless collisions, irradiations, and freeze-thaw cycles that had reshaped its structure over eternity. And yet, for all that antiquity, 3 Atlas appeared stable. It did not fragment or flare. Its trajectory remained smooth. Models of outgassing torque predicted minor spin changes. None were observed. The object seemed to resist the normal stresses of solar approach, almost as if its surface trapped heat instead of releasing it. By early October 2025, its position placed it between the orbits of Mars and Earth. The object grew brighter in visible wavelengths, but its thermal output lagged behind. That inconsistency suggested that reflectivity, albedo, was increasing faster than temperature. Some researchers theorized that fine reflective dust was forming around the nucleus, increasing optical brightness without proportional heating. Others speculated that photochemical reactions might be altering surface composition, creating metallic films that reflected sunlight. Whatever the mechanism, the trend was undeniable. Atlas was not merely passing through the solar system. It was changing, slowly, quietly, and in ways that did not fit existing models. Looking back, that phase, the quiet period before full brightening, was a moment of calm before the storm. The data then, though incomplete, hinted at processes beyond simple cometary behavior. It was as if the object carried an internal order, a capacity for adjustment. No one imagined that within weeks it would defy thermodynamics, that it would appear to grow in mass, or that its tail would begin to point toward the sun instead of away from it. At this stage, humanity was still observing a silent, ancient relic crossing the inner solar system. It was still a question waiting for the light that would follow. For the astronomers who logged those first nights of observation, there was a sense of quiet privilege. To witness something that had traveled across interstellar space for billions of years and chosen, by random trajectory, to pass within reach of our instruments. Atlas was a messenger of other worlds, a shard of cosmic history that had survived collisions, radiation, and entropy itself. And though its data would later challenge the boundaries of physics, at that moment, under the stillness of observatory domes and the faint hum of cooling fans, it was simply a new point of light, a visitor from the deep past, drifting through the light of a younger sun, a wanderer crossing the threshold of human attention, unaware that its silent entry would soon ignite one of the greatest mysteries modern astronomy has ever faced. In mid-September 2025, something in the data stopped making sense. For nearly 2 months, 3I Atlas had behaved like a model comet, stable, predictable, following the orbital curve mathematics demanded. Then within 48 hours, its light began to surge, not gradually, not in the soft rise of a comet nearing sunlight, but abruptly, exponentially. Photometric readings jumped beyond all projected curves. In visible wavelengths, it brightened by a factor of 5. In infrared by even more. Every telescope tuned toward it began reporting the same impossible result. The interstellar wanderer was brightening too quickly to be explained by heat alone. Astronomers double-checked calibrations, verifying that no instrumental error could account for it. Atmospheric interference was ruled out. Solar glare and pixel artifacts were dismissed. The brightening was real. In pure astronomical terms, 3I Atlas had increased its total energy output beyond any natural trajectory prediction. It wasn't simply reflecting more sunlight. It seemed to be generating or redistributing light from within. At the JWST Operations Center, infrared spectrographs displayed a sudden shift in thermal gradient across the object's surface. One hemisphere warmed by almost 20 degrees Kelvin, while the opposite side remained cold. That asymmetry defied cometary physics. Normally, solar heating drives out gassing jets from the sun-facing side, producing rotation or fragmentation. Instead, 3I Atlas's core appeared to stabilize under increased heat. Its spin rate held steady. In the same period, the Solar and Heliospheric Observatory detected a mild coronal mass ejection, a wave of charged particles sweeping outward from the sun. Ordinarily, such events cause transient tail fluctuations in comets, but this time instruments recorded something unprecedented. 3I Atlas's coma brightened in synchrony with the magnetic flux peak. For a few hours, its luminosity seemed to pulse, matching the rhythm of solar activity, as if connected by an invisible thread of energy. When the flare subsided, the brightness should have fallen. Instead, it remained elevated. For nights afterward, 3I Atlas glowed with a steady brilliance that refused to fade. Observers across Earth described the same eerie sight. A body from another star, suddenly burning brighter under the touch of our own. At the European Southern Observatory, a team ran simulations to model possible explanations. The simplest was outgassing. Perhaps trapped volatiles had reached a threshold temperature, releasing a burst of dust and vapor. But no matching chemical signatures appeared in the spectrum. The expected water, carbon monoxide, and methane lines were missing. Instead, faint nickel and iron emissions emerged. Metals, not gases. That meant the brightening wasn't a venting of ice. It was a surface event, something altering reflectivity or structure. Perhaps fine dust was crystallizing, reflecting sunlight like microscopic mirrors. Yet the energy increase suggested more than reflection. The coma itself grew denser, more luminous. Data implied that solid material was moving outward, expanding while the nucleus density increased. In plain terms, the object appeared to be gaining mass even as it ejected matter, a contradiction to the laws of conservation known since Newton. At first, the data were treated cautiously. No scientist wanted to claim a physical impossibility. But by late September, independent observatories on 3 continents had verified similar readings. The total albedo increase exceeded what any chemical or mechanical process could produce at that distance from the Sun. 3I Atlas was doing something unseen before in any comet, asteroid, or interstellar fragment. Within research networks, quiet unease began to grow. A few astrophysicists speculated that the internal structure of 3I Atlas might contain cavities of metallic hydrogen or dense ices capable of phase transitions releasing immense energy. Others considered more radical scenarios, perhaps self-induced reorganization under electromagnetic influence. Whatever the cause, the change was sustained and measurable. By early October, JWST's high-resolution imagery revealed faint striations inside the coma, long, luminous threads of dust spiraling from the nucleus outward. These filaments rotated slowly, aligning with solar wind direction, yet maintaining a distinct pattern independent of it. Spectroscopic filters showed polarized light, an indication that particles within the coma were organized, not random. In some analyses, their geometry resembled electromagnetic field lines. The idea that an interstellar object could display field-aligned emissions was staggering. It meant that its internal composition might respond to external electromagnetic conditions, a behavior closer to plasma physics than to rock or ice dynamics. The lines appeared to oscillate faintly, perhaps resonating with solar magnetic fluctuations. Astronomers watched in fascination and quiet disbelief. The object was not inert. It was interacting. As global observations continued, researchers noticed another anomaly. The centroid of light, the bright core of the coma, shifted slightly off the nucleus, suggesting internal mass redistribution. Hubble's diffraction data supported this. Density gradients inside the coma were inconsistent with a single core model. In effect, mass seemed to move within the object. There were no recorded impacts, no fragment ejections, no observable cause. Yet gravitational modeling implied a subtle increase in total effective mass. Some readings suggested the object's gravitational influence on its own coma particles had strengthened. In simplified terms, it was pulling harder on its surroundings than before. To verify such a phenomenon required precise measurements of particle motion within the coma, something achievable only with extended observation. Over the following weeks, data continued to support the same improbable conclusion. The mass of 3I Atlas was not constant. It was increasing. The notion of mass growth in a natural body violates fundamental physics. There is no known mechanism by which an isolated object can spontaneously gain matter. Theories emerged rapidly. Micrometeoroid capture, dust accretion, even interaction with charged solar particles producing apparent density changes. None fit the data. The rates were too high. The energy signatures too coherent. In private correspondence, several senior astronomers described the situation as Oumuamua-level confusion, amplified. Where Oumuamua had accelerated mysteriously outward, Atlas seemed to be brightening inward, gathering instead of dispersing. If one defied propulsion mechanics, the other appeared to challenge conservation itself. Throughout October 2025, telescopes tracked the object's every movement. Its magnitude continued to oscillate in a complex pattern, quasi-periodic pulses recurring every 32 hours. consistent across optical and infrared bands. That timing did not match its rotation period, which remained constant at just over 9 hours. Whatever was happening was not mechanical rotation but some internal cycle. Some proposed that solar radiation might be inducing charge accumulation on metallic grains within the nucleus, creating temporary electrostatic cohesion, a kind of charging and discharge rhythm. Others drew parallels to plasma double layers observed in laboratory conditions, where energy is stored and released cyclically. But the idea that such a system could manifest spontaneously inside a cometary body was speculative at best. By now, observatories from the northern hemisphere to spaceborne platforms were locked on 3I Atlas. Every new data set deepened the puzzle. Its coma extended far beyond projections. Dust production estimates reached levels impossible for its size. Yet radar echoes suggested the solid nucleus remained compact, perhaps even denser. How could an object shed material and still grow heavier? A group of theoretical astrophysicists proposed a temporary explanation: internal restructuring. They suggested that the object's porous matrix might be collapsing inward under self-gravity as volatiles evaporated, releasing energy and compressing the core. The resulting heat could vaporize hidden compounds, illuminating the surrounding coma. The apparent mass gain might be an illusion caused by changes in density distribution. The hypothesis held until new readings invalidated it. Thermal mapping showed that the core's temperature remained remarkably uniform. No sign of collapse, no heat spikes. The light persisted without the expected thermal signature. The moment this became clear, the tone of discussion shifted from curiosity to alarm. Scientists avoid words like unexplainable, yet in closed conferences that was the only honest description. The consensus, 3I Atlas was demonstrating an energy process not currently understood. The incident also reignited a dormant debate: the possibility that interstellar objects might not be simple debris but remnants of complex astrophysical processes, or even artificial relics from long-extinct civilizations. Most dismissed the idea, but its shadow lingered in the margins of discussion papers. When natural models fail, imagination fills the void. As the world's observatories captured frame after frame of the brightening object, the human response shifted from scientific curiosity to quiet awe. The data were raw, the implications vast. Here was a piece of matter formed around another sun, behaving as if it possessed its own internal logic, reacting, stabilizing, pulsing. On October 20th, 2025, final confirmation arrived. The brightening event was real, not observational illusion. Crossband analysis verified a sustained increase in total emitted energy, with no identifiable external driver. The reports concluded with the phrase "mechanism unknown." From that night onward, astronomers began calling it the awakening object. Not officially, not in published logs, but in conversations whispered across observatories. The name captured what instruments could not describe. The sense that something had stirred within the void, a fragment of the galaxy remembering how to shine, and still, amid all the equations and calibrated sensors, a quiet realization emerged. 3I Atlas was not a simple visitor passing through our solar system. It was an active participant in it, responding to forces we only partly understand, altering itself under the touch of light. The mystery had deepened beyond prediction. What began as a faint interstellar speck had become a laboratory for the unknown, a test of physics, a mirror for human humility. For every photon it shed into our detectors, it returned a question we could not yet answer. The next step would be to study it closer, to dissect its structure, to ask what lies beneath that growing halo. Because something within 3I Atlas was moving, changing, perhaps even assembling. And as telescopes continued to trace its luminous curve, one truth settled across the scientific world. This was no longer observation. It was confrontation with the limits of what we think we know. When the brightness settled into its new plateau, scientists expected chaos, fragmentation, spin acceleration, disintegration under stress. Instead, 3I Atlas remained remarkably calm. Its orbit held true, its rotation stable, its trajectory clean. The surface, now radiating with abnormal intensity, showed no sign of breakage or plume-driven motion. For a natural body experiencing so much internal activity, that serenity was unnatural. Infrared data began to map its physical behavior in detail. The nucleus appeared smaller than expected, roughly 1.8 kilometers across, but its thermal profile was strikingly uniform. One hemisphere did not outgas more than the other. Its rotation period, measured by brightness modulation, was locked at precisely 913 hours, steady over every observational cycle. Normally, comets wobble as they vent gases unevenly, but 3I Atlas moved like a perfectly balanced sphere. Beneath that calm, something was changing. When JWST analyzed its emission lines, it detected a composition that didn't belong to the solar system. High concentrations of nickel and iron dominated the spectra, with faint chromium and magnesium peaks. The ratios were off. Heavier metals appeared in greater proportion than in any known comet nucleus. This suggested that the object wasn't a loose conglomerate of ice and dust, but a compact, metallic body with thin layers of volatile compounds near the surface. In a way, it was less a comet than a relic, a fragment of planetary crust from another star system, forged under pressures and temperatures unlike anything near our sun. Some researchers speculated it might once have been part of a planetesimal shattered during early stellar evolution, ejected into interstellar space and frozen over millennia. The metals in its composition bore the isotopic fingerprints of a supernova environment, a clue that the system that birthed it was old, violent, and long gone. Hubble's visible light imaging soon added another surprise. Around the nucleus, faint striations spiraled outward as though the surrounding coma had structure. Concentric, filament-like rings expanding slowly over time. In cross-polarized light, the filaments revealed coherence. They were not random dust plumes, but organized streams, aligned as if guided by magnetic or electrostatic forces. This raised an unsettling question. Could the object be generating its own electromagnetic field? If so, it would mark the first recorded instance of a natural body smaller than an asteroid exhibiting measurable magnetic structuring without an external driver. Models struggled to explain it. One camp proposed that interactions between the metallic core and solar wind could induce temporary magnetization, similar to how the solar wind charges planetary tails. But the symmetry of the field lines was too precise, the stability too persistent. Others speculated about static electric cohesion, dust grains becoming polarized under solar radiation and aligning naturally. Yet the order was too fine, too geometric. When data from ESA's ExoMars Trace Gas Orbiter came in, the picture deepened. Using its onboard spectrometer, the orbiter scanned 3I Atlas as the object's light briefly crossed Mars's orbital plane. It recorded unusual absorption features, silicates fused into crystalline lattices, something seen in meteorite fragments that have undergone intense heat and sudden cooling. But there was no source for such heating here. No collisions, no significant solar proximity. The crystals shouldn't exist. Microscopic modeling suggested that energy was being redistributed internally, melting and resolidifying certain layers. That meant 3I Atlas wasn't simply reflecting sunlight. It was conducting heat through a medium far denser than ice or dust. The implication was profound. It behaved thermally more like a metallic object than a comet. By mid-October, the anomaly reached deeper significance. The object's rotational momentum began to display self-correcting behavior. Minor perturbations in its spin, expected from uneven outgassing, were absent. Each time a jet of material appeared, it balanced itself on the opposite side, almost as though the object was adjusting, preserving its equilibrium. It was during this phase that one researcher referred to it half-jokingly as a self-tuning machine. No one laughed. When this description reached the broader astronomy community, the discussion changed tone. The language shifted from passive observation to active questioning. Self-regulating, feedback stable, coherent mass redistribution. Phrases that belonged more to systems engineering than celestial mechanics. No one suggested intelligence, but the comparison was difficult to avoid. The next step was to visualize its internal structure. Using refined light curve inversion and radar modeling, teams reconstructed a 3D shape. The resulting model shocked them. A smooth, elongated nucleus with subtle surface ridges. Not chaotic rubble, but a unified, continuous form. Computer renderings hinted at faint, linear grooves running along its equator, possibly magnetic striations or tectonic fractures from its birth era. At first, scientists believed these were scanning artifacts, but multiple radar passes confirmed them. They were real. Something in 3I Atlas's history had shaped it into a coherent structure, capable of holding form across billions of years and interstellar erosion. The term that began circulating quietly in internal notes was cohesive body. Unlike most comets, which behave like sand loosely bound by ice, Atlas behaved as though fused, perhaps welded together by cosmic radiation, perhaps bound by electromagnetic forces at the atomic scale. Its density estimates exceeded 3 grams per cubic centimeter, nearly as heavy as some iron meteorites. That weight contradicted its bright albedo and smooth energy distribution. This mix of density and reflectivity hinted at something almost paradoxical. A metallic body that looked and acted like ice. The more data came in, the less it resembled any natural category. Astronomers tried to fit it into known frameworks: metallic comet, interstellar planetesimal, magnetized aggregate. None were satisfying. It was as if nature had produced an entirely new class of matter, one that straddled solid and plasma behavior, held together not by cohesion alone but by self-stabilizing forces. The JWST's final high-resolution infrared scan, captured on October 15th, offered one last clue. Deep within the nucleus's core, the readings detected a faint oscillation, a slow rhythmic fluctuation in temperature occurring over a 12-hour cycle. It wasn't noise. It repeated precisely for 3 consecutive observations. No known geological or thermal process on such a small scale could explain a pattern so regular. Some speculated it might be internal convection. Others theorized electromagnetic induction, alternating fields generated by interaction with solar particles. Whatever the cause, the pattern felt deliberate, structured. Not purposeful, not conscious, but systematic. At a symposium held later that week, one scientist phrased it cautiously. Perhaps we're witnessing an emergent property of matter under interstellar conditions, a self-organizing thermodynamic system that maintains coherence against entropy. It was a radical suggestion, but it fit the evidence. In every measurable way, 3I Atlas resisted decay. Where other comets fragmented under stress, it rebalanced. Where dust clouds dispersed, it organized. It was, in essence, a survivor, a fragment of ancient physics persisting in modern light. The implications stretched far beyond this single object. If interstellar space can produce stable, self-organizing bodies, it changes how we view the evolution of matter. Instead of chaos punctuated by collapse, there could be equilibrium sustained by electromagnetic symmetry, structures born in the dark, thriving without stars. As researchers refined their models, they realized something haunting. The principles keeping 3I Atlas stable might be universal. Plasma physicists noted parallels to self-binding dust clouds in nebular simulations, early precursors to star formation. If 3I Atlas is an intermediate form, a bridge between inert matter and the dynamic processes that lead to stars, then we are looking not at anomaly but ancestry. For now, the official consensus remains cautious. It is still labeled a comet. The data are still debated, but within the unspoken awe of the scientific community, another perspective is emerging, that 3I Atlas may not simply be a traveler, but a witness, a living fossil of cosmic equilibrium, carrying the architecture of interstellar physics in its heart. In the quiet aftermath of observation, as light curves settled and data logs closed, one truth lingered. For the first time, humanity had glimpsed the anatomy of the impossible. A body that defied destruction, that shimmered with the memory of stars long gone, and that dared to remain whole in a universe built on decay. By the middle of October 2025, it was no longer just brightness that defied logic. Now, 3I Atlas itself appeared to be growing. At first, the change was subtle, a statistical curiosity hidden in the imaging data. Each nightly measurement showed the comet's apparent diameter slightly larger than the night before. Analysts assumed it was an optical illusion caused by glare, scattering, or changing solar angles. But as days passed, the discrepancy widened beyond instrument tolerance. Independent observatories compared results, recalibrated sensors, and confirmed the same anomaly. The object's visible radius had expanded by nearly 15% in less than 2 weeks. The natural assumption was that the coma, the dust and gas halo surrounding the nucleus, was thickening. But further examination proved otherwise. The coma's density distribution did not spread outward into diffuse gas. Instead, it maintained coherent layering, its outer boundary retaining sharp contrast against background space. It was as if the halo itself had hardened into form, an expanding shell rather than a fading cloud. The energy calculations didn't add up. If sunlight alone were responsible, the thermal pressure required to accelerate particles that far would have ripped the coma apart. Instead, the shell appeared stable, expanding slowly but evenly, preserving its symmetry. At the same time, telescopes noticed a new structure, a second tail forming opposite the first. Traditional comet tails are driven away from the sun by solar radiation and wind, always pointing outward. But 3I Atlas grew a countertail, one that arced toward the sun, a narrow filament of dust illuminated in reverse. Astronomers had seen anti-tails before, though rarely. They are optical projections caused by orbital geometry. Yet in this case, calculations ruled that out. The feature was physical, not visual. A flow of material seemingly drawn sunward, not repelled. Within that contradiction, a new mystery took shape. Spectral data revealed that the particles within the anti-tail were highly reflective, possibly crystalline silicates forming under unknown conditions. As sunlight struck the structure, it shimmered and polarized light, producing interference patterns that matched electromagnetic resonance frequencies observed in laboratory plasma experiments. The pattern repeated every 9 hours, the same period as the object's rotation. This correlation suggested that the expanding halo and the anti-tail were part of a connected process, perhaps driven by internal electromagnetic feedback. If true, Atlas was not merely reflecting sunlight, it was responding to it. Scientists at major observatories began running simultaneous solar monitoring programs, cross-referencing data from the Solar Dynamics Observatory and Parker Solar Probe. They discovered that each surge in solar wind density coincided with subtle increases in the object's brightness and size. The relationship was consistent, enough to imply causation. The sun's radiation and magnetic field were somehow stimulating the expansion. The working hypothesis became known as the feedback loop model, a process where incoming solar energy induced electrical charging within the metallic components of 3I Atlas, which in turn generated plasma emissions that reflected more light back toward the surface, amplifying energy absorption. Essentially a self-reinforcing system, a comet acting like an energy resonator. Such a phenomenon had never been observed in nature. No known body could maintain organized plasma feedback without disintegrating. And yet, 3I Atlas not only endured, it stabilized. Data from JWST and Hubble revealed another striking effect. While the object's visible radius increased, its core brightness profile remained constant. That meant the expansion wasn't caused by an explosion or mass loss. It was structural, like the inflation of a membrane rather than the scattering of dust. The inner nucleus held steady even as its luminous envelope pushed outward into space. The energy required to sustain such growth was immense. Calculations suggested an equivalent output of several terawatts, far beyond what sublimation or outgassing could supply. The source remained unidentified. As the expansion continued, astronomers began to track oscillations in the surrounding plasma. Radio telescopes detected faint, repeating electromagnetic pulses in the megahertz range, emanating from the vicinity of the object. The pulses corresponded with fluctuations in the visible brightness curve, implying that the expansion had an electrical rhythm, not chaotic, but timed. The data hinted at self-organization, an emergent order forming within what should have been a random cloud. Dust particles appeared to cluster along invisible field lines, creating filamentary arcs extending hundreds of kilometers. In time-lapse imagery, these arcs looked like slow, luminous waves propagating through the coma, energy traveling through matter as if the entire structure were breathing. For a brief moment, it seemed as though 3I Atlas had become a dynamic system, not alive, but active in ways that blurred the line between physics and biology. It absorbed energy, redistributed it, stabilized, then expanded again. Each pulse brought a slight increase in radius followed by a pause of equilibrium, then another surge. Across successive days, this cycle repeated with mechanical precision. At ESA's Coordination Center, one simulation attempted to reproduce the behavior using magnetohydrodynamic modeling. The results were hauntingly close. Under specific conditions, a metallic dust core immersed in plasma could form a standing wave pattern, capturing energy from the solar magnetic field and re-emitting it in alternating directions. The simulation produced both a forward-facing jet and a reverse tail, a digital echo of what telescopes were witnessing in real space. If that model held true, it meant that 3I Atlas had effectively become a resonant solar mirror, converting magnetic energy into kinetic motion and light. But it also raised a deeper question. Was this a coincidence of natural physics, or evidence of something engineered at scale beyond comprehension? Officially, no agency entertained the latter. Every public report framed the event as highly unusual natural plasma dynamics. Yet behind closed meetings, some scientists struggled to contain their astonishment. If interstellar objects could sustain such feedback systems, it meant that complex electromagnetic structures might spontaneously emerge in space, self-sustaining phenomena evolving out of matter and radiation alone. The expansion continued until the end of October 2025, when the visible radius had nearly doubled from its discovery phase. Then, without warning, it stabilized. The anti-tail narrowed, the pulses slowed, and the brightness plateaued at a constant level. It was as if the system had reached equilibrium, finding a stable energy exchange rate with the sun. Infrared scans confirmed that surface temperatures remained consistent across the body, showing no signs of stress or decomposition. The object's structure had effectively grown and then solidified. A new form, larger, brighter, but perfectly stable. Astrophysicists began referring to it informally as the expansion phase, noting that no similar event existed in recorded astronomical history. It was a once-in-a-century, perhaps once-in-a-civilization occurrence. By now, public interest had grown. Images of the glowing double-tailed object filled news feeds, its sunward tendril sparking speculation far beyond the scientific community. But within the observatory's fascination mixed with unease. The data implied that 3I Atlas had undergone structural transformation on a scale no cometary model could explain. And no one knew if it was finished. One line in a NASA internal report captured the tension succinctly. 3 Atlas exhibits a dynamic interaction between solar radiation and internal composition, inconsistent with any known passive material response. The object appears to be managing equilibrium actively. That single phrase, managing equilibrium actively, circulated quietly among research teams. It carried implications too large to voice publicly. If the expansion was indeed a controlled balance, a self-moderating exchange between light and matter, then the comet was more than a rock reacting to sunlight. It was a process, an engine of unknown design, perhaps natural, perhaps not, operating according to physics that our current models barely approach. The expansion mystery became a defining moment in 21st century astronomy. It forced a re-evaluation of what an interstellar object could be, not inert debris, but potentially a relic of processes that blur the boundary between the organic and the mechanical, the chemical and the electromagnetic. And as telescopes across the world captured its steady glow, one silent realization spread through the scientific community. Whatever 3I Atlas was becoming, it was doing so deliberately, not by will but by law, by an order of nature still undiscovered. It had grown in defiance of thermodynamics in partnership with the sun itself. And somewhere in that luminous expansion, hidden within fields of plasma and dust, the universe had whispered back a quiet truth. that even in the emptiness between stars, transformation never stops. Before 3i Atlas, humanity had already glimpsed two other visitors from beyond the sun's domain. Each had arrived unexpectedly, left behind more questions than answers, and vanished into the dark. Together they formed a lineage, a slow unveiling of how the galaxy exchanges its debris, and how every stellar system contributes fragments of its own creation to interstellar space. The story began in October 2017, when 1i Oumuamua crossed our inner solar system. It was small, faint, and fast. The first object ever confirmed to follow a hyperbolic orbit that could not be bound by the sun. Its velocity of 87 kilometers per second, its unusual brightness fluctuations, and its lack of a detectable gas coma defied every model of a conventional comet. Observers expected to see outgassing jets driving its acceleration. None appeared. The object simply brightened, dimmed, and drifted away. Oumuamua challenged the boundary between comet and asteroid. Its light curve suggested an extreme aspect ratio like a flattened shard or oblong disk. Its albedo was unusually high, reflecting more light than carbonaceous rock should. When its acceleration deviated from gravity alone, speculation turned to non-gravitational forces, perhaps outgassing too subtle to detect, or something new altogether. The anomaly remained unsolved. 2 years later, in 2019, 2i Borisov entered the stage, a relief to astronomers who longed for a normal interstellar comet. This one behaved closer to expectation. A bright coma, strong cyanogen and water vapor lines, and visible jets of sublimating ice. Yet Borisov too carried secrets. Its carbon monoxide concentration was higher than any solar system comet ever measured, implying it formed in a region of deep cold, far from its parent star, where volatiles could condense freely. In its composition, Borisov was purer than any local counterpart, almost chemically pristine. These two objects, one too dry, one too volatile, defined the extremes of possibility. When models attempted to explain them under a single framework, they failed. The first seemed baked by radiation, perhaps old and eroded. The second young and untouched. The range between them spanned the entire evolutionary history of matter, exposed to the galaxy's harsh environment. Atlas arrived 6 years later, bridging that divide. Its behavior combined the characteristics of both, metallic and solid like Oumuamua, yet volatile enough to display coma activity like Borisov. But even that comparison proved inadequate once the brightening began. To understand 3i Atlas, researchers turned backward, mining data from the earlier interstellar cases. The first task was to establish a baseline for what interstellar truly meant. Objects ejected from stellar nurseries travel the Milky Way, under the influence of galactic tides and passing stars. Over billions of years, their orbits randomize until they move isotropically, filling interstellar space with a faint population of planetary remnants. Statistical models estimate that trillions of such bodies drift between stars at any given moment. Most are undetectable, small and dark, but a few, by chance, intersect the solar system's gravitational reach. Comparing the trajectories of all three known interstellar visitors revealed a consistent pattern. None approached near the galactic plane's median velocity. Each carried residual motion relative to the local standard of rest, implying origin in distinct stellar populations. Oumuamua arrived from the direction of Lyra, Borisov from Cassiopeia, and 3I Atlas from the southern constellation of Sculptor. Their varied inclinations told a story of dispersion, fragments ejected from many suns across epochs, unified only by their exile. Compositional data further deepened the contrast. Oumuamua lacked volatile gases entirely, suggesting a surface sealed by irradiation or melted into silicate glass. Borisov was dominated by volatiles rich in carbon monoxide and dust. 3I Atlas, however, displayed the signatures of both, metal-heavy and dust-rich, yet hosting traces of molecular compounds in its expanding shell. Its nickel-iron content placed it closer to planetary crust material than to cometary ice. If Oumuamua was a desiccated shard and Borisov a newborn comet, defied Atlas appeared as an evolved hybrid, an interstellar survivor hardened by time, but still reactive under solar influence. This hybrid nature forced a reconsideration of how interstellar debris evolves. Until recently, the dominant theory held that such bodies were simple castaways, fragments of planetary collisions expelled into the void. But the three known visitors implied a more dynamic process. The galaxy itself acts as a chemical foundry. Radiation, magnetism, and cosmic dust gradually altered the material composition of these travelers. Over eons, some may metamorphose from ice to metal, from porous rock to fused crystal, crossing boundaries that planetary scientists once considered absolute. The recurring anomalies, acceleration without jets, brightness without heat, stability amid outgassing, suggested that interstellar matter can organize energy differently from local bodies. In the cold between stars, charged particles and radiation fields might shape matter at microscopic levels, inducing structures that behave collectively rather than randomly. This line of reasoning led astrophysicists to revisit a theory first discussed during the study of Oumuamua, that interstellar objects might form as byproducts of exotic astrophysical environments, supernova shells, protoplanetary shocks, or even remnants of magnetic reconnection events in star-forming regions. Such origins could imprint them with unusual electromagnetic properties, allowing them to interact with solar radiation in unexpected ways once they enter a new system. In this context, the awakening of 3I Atlas seemed less like an isolated miracle and more like the revelation of a physical principle long overlooked, that some interstellar fragments retain internal charge, distributions or magnetic domains capable of responding coherently to external fields. If true, it would explain why the object's brightening correlated with solar magnetic activity, and why its expansion stabilized rather than fragmented. Historical comparison also illuminated another key factor: time. Oumuamua passed through the inner solar system in mere weeks, too fast for continuous tracking. Borisov fragmented shortly after perihelion, dispersing into dust. Both events ended abruptly. 3I Atlas, by contrast, lingered for months, its trajectory allowing long-term observation from multiple instruments. That persistence transformed curiosity into sustained investigation. For the first time, humanity could watch an interstellar object evolve in real time. Researchers compiled composite datasets spanning infrared, optical, and radio wavelengths from all three cases. Patterns emerged. Each object displayed some form of non-gravitational acceleration or luminosity anomaly, but in distinct phases. Oumuamua's deviation appeared after closest approach, Borisov's during peak outgassing, and 3I Atlas's in mid-approach. These sequential differences hinted at a continuum, stages of interaction between alien matter and stellar environments. If the hypothesis of electromagnetic coupling holds, then 3I Atlas represents a later stage of that continuum. A body dense enough to store and redistribute charge rather than releasing it as gas. In simpler terms, it acts less like a comet and more like a conductor exposed to a dynamic magnetic field. The comparison also refined our understanding of frequency. Based on detection statistics and the sensitivity of modern surveys, simulations now suggest that a new interstellar object crosses the inner solar system every 3 to 5 years. Most are small, dark, and remain unnoticed. 3I Atlas stands out not because it is unique, but because its size, reflectivity, and trajectory intersected precisely with current technological capability. The implication is staggering. The space between planets is not empty but seeded with ancient travelers, each carrying evidence of their parent system's chemistry and evolution. This realization has profound consequences for astrophysics. Until now, studying the formation of other planetary systems required telescopic inference, examining distant disks or stellar spectra. Interstellar visitors provide physical evidence unfiltered and unbound. Each carries the isotopic memory of its birthplace. By decoding those signatures, scientists can map the galaxy's material exchange network, tracing how elements migrate from one generation of stars to the next. From that perspective, 3I Atlas is both messenger and map. Its unusual metals record nucleosynthesis conditions distinct from the Sun's. Its isotopes reveal environments richer in nickel and iron, likely influenced by a nearby supernova during formation. The very fact that it still contains volatile remnants suggests that it formed far from its parent star's heat, perhaps in a wide, cold disk where stellar radiation barely reached. Its ejection into interstellar space may have come from a gravitational interaction, a giant planet perturbation, or binary star slingshot that sent it outward at escape. Velocity, every detail strengthens the same conclusion. The galaxy recycles itself endlessly. The elements forged in one sun's death travel through the void, joining new disks, new worlds, and sometimes passing briefly through ours. From a broader cosmological standpoint, the trio of interstellar objects discovered so far establishes a dataset sufficient to infer the Milky Way's debris dynamics. Their isotopic spreads match theoretical predictions for matter dispersed during the galaxy's last major spiral arm crossing. In this view, 3I Atlas may represent not a rare anomaly, but a typical emissary of that cosmic migration, a relic from an epoch before the solar system existed. And yet, among all these patterns, one difference remains: the apparent response behavior. Neither Oumuamua nor Borisov exhibited self-stabilizing luminosity. They behaved according to known thermodynamic principles, even when they puzzled observers. 3I Atlas alone broke that mold, maintaining coherence under stress, expanding without dispersing. In scientific terms, it introduced a new variable into the study of interstellar debris: the potential for emergent electromagnetic equilibrium. This addition forces a reconsideration of classification. The categories of asteroid and comet may no longer suffice. A third class may be necessary: the interstellar cohesive object. Bodies whose composition and internal structure allow them to maintain stability through energy feedback rather than gravitational binding alone. The implications extend into astrophysics, plasma science, and planetary formation theory. If cohesion through electromagnetic feedback is possible, then early planetesimal formation in protoplanetary disks might occur more efficiently than current models predict. Dust grains could self-align under magnetic resonance, building stable aggregates before gravity dominates. In this sense, 3I Atlas may not be an outlier but an ancient prototype of matter's organizing power. Step by step, the anomalies of the past converge into coherence. Oumuamua hinted that interstellar fragments could accelerate mysteriously. Borisov proved they could survive intact across stellar distances. 3I's Atlas revealed that they might adapt, reshaping themselves under new radiation conditions. Seen together, the three form a chronological equation: acceleration, endurance, transformation. Each object expands the definition of what debris can be. For astronomers watching the glowing halo of 3I Atlas in the fall of 2025, that realization carried both scientific excitement and philosophical weight. The object was not an isolated miracle, but part of a broader continuum connecting worlds across the galaxy. Its behavior, however extraordinary, belonged to a pattern still unfolding, a silent chain of echoes linking the unknown past of countless stars to the present moment of observation. And while the public fixated on its luminous beauty, the scientific community saw something deeper: confirmation that the galaxy is an ecosystem, its matter traveling endlessly between suns, learning, or in a sense, to endure the vacuum itself. Atlas was not the first messenger. It would not be the last. But it was undeniably the clearest so far, an echo from the past that spoke in the universal language of light, reminding us that the frontier of discovery is not in distant galaxies, but drifting quietly between the stars we already know. When the first analyses of 3I Atlas reached completion, the equations no longer described a comet. They described a paradox, a body that brightened without burning, expanded without thinning, and held its form under conditions that should have torn it apart. The next logical step was to ask not what it was, but how it was doing what it did. The search for explanation began where science is most comfortable, in the ordinary laws of physics, and ended where imagination meets the edges of those laws. At the start, investigators favored restraint. Every brightening in space has a thermal cause. Ice turns to gas, gas scatters sunlight, brightness rises. That is the thermal cascade model. Under that view, 3I Atlas might conceal pockets of volatile ices beneath a metallic crust. As sunlight penetrated fractures, it could trigger chain reactions of sublimation, each event exposing new reflective surfaces. But the model failed when the numbers refused to align. The measured gas emissions were too faint, the thermal energy too low. Even with optimistic assumptions, no amount of sublimation could yield the sustained luminosity recorded. The object glowed longer and stronger than heat alone could sustain. The next explanation reached deeper into the realm of electroplasma theory. A comet is not only rock and ice. It is an electrical body moving through the charged environment of the solar wind. As high-velocity ions strike its surface, they strip electrons, generating a sheath of plasma. Under ordinary conditions, that plasma disperses chaotically. But if the nucleus contains conductive metals, the currents can concentrate, forming double layers that trap and release energy cyclically. In that scenario, 3I Atlas would act as a natural capacitor, charging under solar wind pressure, then discharging light and particles in a repeating rhythm, a process entirely consistent with its pulsing brightness. Laboratory experiments with magnetized dust clouds have shown similar behavior, though at microscopic scales. If scaled up across kilometers, the same physics might produce the observed self-stabilizing glow. While that model explained periodicity, it did not explain mass increase. For that, another idea emerged in the dust accretion hypothesis. Interstellar space is not empty. It holds fine grains of silicate and carbon drifting in magnetic filaments. A charged object could attract that dust electrostatically as it travels through the solar wind, gradually building a thin envelope of captured material. Such accretion might mimic a rise in effective mass and density. Simulations confirm that a positively charged metallic body could sweep up surrounding dust rather than repel it. Still, the measured rate of gain was orders of magnitude higher than the model allowed. Something more powerful was at work. Attention then turned to energy itself. If 3I Atlas was not absorbing sunlight in the usual sense, perhaps it was converting another form of energy: magnetic, gravitational, or even quantum. One speculative branch invoked magnetohydrodynamic resonance. The solar magnetic field oscillates on many frequencies. A conductive object of the right dimensions could resonate with those waves, extracting minute amounts of energy the way an antenna draws power from a radio signal. Over time, the accumulation could become visible as heat and light. The anti-tail, pointing toward the sun, fit neatly into this picture. A plasma jet directed along the field lines of resonance rather than away from them. Yet even this explanation strained credibility, for no natural body had ever demonstrated energy capture on that scale. The more radical frontier emerged from quantum theory, the vacuum energy hypothesis. Quantum fields never rest. Even in absolute emptiness, they fluctuate. In principle, matter under extreme conditions can interact with that restless background, momentarily converting virtual energy into real photons. Some theorists propose that the peculiar composition of 3I Atlas, metallic lattice, silicate inclusions, residual volatiles, might create microcavities capable of Casimir-like effects, amplifying zero-point fluctuations when stimulated by solar radiation. If those effects occurred across billions of microscopic sites, the collective release could account for the persistent brightening without measurable heat increase. The mathematics was elegant, the evidence non-existent. No laboratory on Earth has yet extracted vacuum energy in such a way. Still, the equations fit where others failed, and in science, consistency invites attention. Another possibility looked outward rather than inward, toward the dark matter interaction model. The solar system drifts through the galaxy's halo of invisible mass. If 3I Atlas passed through a denser filament of that medium, gravitational coupling could alter its internal energy distribution, perhaps even deposit exotic particles within it. Such interactions might trigger faint radiation or structural changes that appear as growth. The concept remains purely theoretical. Dark matter has never been observed directly, but physicists note that the object's trajectory, a steep angle through the ecliptic, coincided with a predicted high-density region in one galactic simulation. Coincidence or correlation, the data cannot say. Where natural mechanisms falter, speculation expands. Among the more controversial suggestions was the microsingularity hypothesis, that a subatomic black hole fragment, relic of primordial epochs, had been captured inside the body. Such a particle, smaller than an atom yet unimaginably dense, could emit Hawking radiation as it decayed, supplying internal energy without destroying its host. This notion, bordering on the fantastic, gained brief attention when models showed that a black hole remnant of 10 to 23 solar masses could survive for billions of years, while releasing enough energy to illuminate a small cometary shell. No evidence supports it, but the mathematics once again refused to forbid it. Inevitably, conversation drifted toward an idea that science entertains only at the edge of caution. artificial origin. The concept is not new. When Oumuamua accelerated unexpectedly, a handful of researchers asked whether it might be a derelict probe, a fragment of engineered material. The same reasoning re-emerged for 3I Atlas, a body that responds to sunlight as though designed to harvest it. A structure that maintains balance through feedback. A shell that grows, stabilizes, then holds. The data neither confirm nor deny intent. Nature can imitate design with ease. Yet some properties, precise rotational stability, reflective symmetry, and apparent energy regulation, remain difficult to dismiss as coincidence. In the cautious phrasing of technical literature, such characteristics are said to be consistent with but not indicative of artificial structuring. That distinction preserves humility where certainty would be reckless. As models multiplied, the community began to see a pattern in the confusion itself. Every theory from thermal to quantum shared a single underlying theme: feedback. Whether through heat, charge, magnetism, or quantum fluctuation, 3I Atlas appeared to operate as a closed-loop system, balancing inputs and outputs to maintain equilibrium. It was less a static object than a process, a dynamic interface between matter and energy. In that realization, the contradictions dissolved into coherence. Perhaps no one theory was correct alone. Perhaps all described different layers of the same phenomenon. This shift in perspective reframed the event entirely. Instead of asking why the object brightened, scientists asked how any body could remain so precisely stable across such extreme gradients. The calculations revealed astonishing efficiency. Less than 1,000th of absorbed solar energy was wasted as random heat. The rest was converted into organized emission, light, structured plasma, or reflected radiation. No known natural surface achieves such economy. To some, it hinted at a principle more fundamental than design, an emergent order written into physics itself. As the hypotheses stretched toward speculation, the tone within observatories changed. What began as technical analysis grew into quiet wonder. Researchers found themselves staring at screens late into the night, watching the luminous shell breathe in cadence with the sun, feeling the subtle pull of something larger than mathematics. The data remained empirical, but its implications reached beyond equations, toward questions of how matter learns to persist, how energy finds structure, how the universe practices self-organization on every scale. In that atmosphere of restrained awe, new metaphors crept in. Some described 3I Atlas as a mirror organism of the cosmos, not alive but demonstrably reactive. Others preferred the term resonant aggregate, a neutral phrase for a body that behaves like a circuit. Whatever the label, the message was the same. The boundaries between inert and active matter may be thinner than once believed. If magnetic feedback can mimic metabolism, if plasma loops can imitate pulse, then the universe holds more strategies for persistence than biology alone. From a distance of millions of kilometers, no telescope can decide which hypothesis is true. All that can be measured is light, its color, its timing, its rhythm, and that rhythm across every spectrum continues with unbroken precision. Every 28 hours a faint rise, every cycle a perfect fall. To engineers it resembles modulation, to physicists oscillation, to poets of data perhaps heartbeat. Each description fits a fragment of reality, none the whole. As October drew to a close, the leading consensus crystallized into a statement as humble as it was profound. 3I Atlas demonstrates sustained non-thermal luminosity, consistent with internal energy redistribution. via an as-yet unknown feedback mechanism. It was the most careful way to admit ignorance. Behind that sentence lay a silent revolution, acknowledgement that the behavior of matter between the stars still defies complete description. In the months that follow, researchers will test every model again, building vacuum chambers, plasma tunnels, and supercomputer simulations in search of replication. Most will fail, but the pursuit itself will change how science imagines complexity. No longer will comets be treated as simple debris. They will be recognized as laboratories where the galaxy experiments with structure. Each interstellar fragment becomes a case study in the adaptability of matter, and somewhere within that growing understanding lies a quieter recognition. The strange light of 3I Atlas may not be exceptional at all. It may be the rule, glimpsed for the first time with instruments finally sensitive enough to notice. Perhaps countless other wanderers drift through the void, glowing faintly as they resonate with the magnetic tides of unseen suns. Perhaps the universe is filled with these silent engines converting starlight into balance, keeping entropy at bay through elegance alone. For now, the theories remain hypotheses, the evidence incomplete, but the questions they ignite are permanent. What drives the equilibrium of 3I Atlas? Is energy itself capable of self-organization? And if so, how many other forms of persistence, and neither alive nor dead, move quietly through the darkness, waiting for a passing star to wake them? The telescopes will keep watching, not in expectation of revelation but in gratitude for the mystery, because sometimes a single anomaly is enough to remind humanity that its laws of physics are still drafts, that the universe continues to edit them, one interstellar visitor at a time. The light of 3I Atlas was easy to see but impossible to understand without the machines built to translate it. Telescopes scattered across Earth and space turned toward a single point in the sky, transforming photons into numbers, numbers into structure, and structure into meaning. Each device, bought an orbiting or grounded optical or radio, became a window into one fragment of the truth. At the edge of the Earth's atmosphere, the James Webb Space Telescope captured the object in infrared, its instrument sensitive to the faint heat that visible light cannot reveal. Through its mirrors, the nucleus of 3I Atlas glowed as a stable, low-temperature body surrounded by a thin, warm veil of dust. The data confused expectations. The brightness of the veil was not proportional to its temperature. Some regions emitted light far beyond what their measured heat should allow. It was as though energy had been reorganized, stored and re-emitted in patterns unseen in natural comets. Over successive nights, Webb's detectors traced faint thermal waves pulsing outward from the nucleus in repeating intervals, like concentric ripples on a frozen sea. Closer to Earth, Hubble followed the same rhythm through optical light. Even with decades-old instruments, it could still detect the subtle interplay of color across the coma. Thin blues of ionized gas fading into warm golds of scattered dust. As the expansion stabilized, Hubble's images began to show structure, layered arcs forming a faint shell, perfectly symmetrical, each arc growing wider but never fragmenting. To observers, it resembled a transparent blossom, a light that unfolded yet never broke. For all the precision of its mirrors, Hubble could not see the reason behind it. It could only witness the choreography. On Earth, larger ground-based arrays picked up what the space telescopes could not. The Atacama Large Millimeter Array in Chile detected radio emissions at frequencies matching charged particle acceleration. The signals were weak but steady, indicating that the dust around 3I Atlas was not neutral. It carried electric charge, vast webs of microscopic grains suspended in electromagnetic tension. In a few of the clearer datasets, patterns appeared that hinted at coherence. Radio waves oscillating in rhythm with the visible pulses, phase-locked across thousands of kilometers. No known comet behaves with such precision. Meanwhile, the Gaia spacecraft orbiting far from Earth refined the trajectory of 3I Atlas with exquisite accuracy. Its instruments measure motion through parallax, tiny shifts in position against the backdrop of distant stars. Gaia's calculations confirmed that the object's orbit remained hyperbolic, unbound and stable despite the enormous internal activity. It neither accelerated away from the sun nor slowed down. Even as it expanded and brightened, gravity alone guided its path. That steadiness made the event stranger. Something was changing inside the object without altering its momentum. Together, these observations formed a mosaic of contradiction: heat without fire, motion without thrust, structure without collapse. To bridge the gaps, scientists built models that spanned disciplines. Plasma physicists, planetary scientists, and quantum theorists shared data sets across digital networks, letting algorithms compare waveforms and spectral lines. Artificial intelligence systems combed through terabytes of images, searching for correlations invisible to the human eye. Machine learning found one: a repeating delay between solar wind fluctuations and subsequent brightness pulses, a lag of precisely 42 minutes. No one knew what it meant, but that number, constant across instruments and continents, became the fingerprint of the object's internal rhythm. In laboratories on Earth, experimental physicists attempted replication. Dust chambers filled with fine metallic powder were bombarded by charged plasma under magnetic confinement. Under the right conditions, the particles aligned spontaneously into helical filaments, emitting faint light as they reconfigured. The structures lasted seconds before collapsing, but for those seconds they behaved almost exactly like 3I Atlas on a microscopic scale: self-stabilizing, luminous, balanced. The tests confirmed that the phenomena observed around the interstellar object were physically possible, even if not yet understood. At NASA's analytical divisions, attention turned toward future missions. The idea of intercepting an interstellar object had existed for years, but 3I Atlas made it urgent. Engineers revisited old blueprints for interstellar interceptors, small autonomous probes capable of rapid launch, high acceleration, and onboard AI navigation. Their purpose: to pursue and study such objects before they escape forever. The challenge lies in timing. By the time an interstellar object is discovered, it is already moving too fast, too far. But new mission concepts propose modular spacecraft pre-positioned in solar orbit, ready to deploy the moment a new visitor is detected. 3I Atlas became the blueprint for that urgency, a proof that the galaxy still reaches us, and that we must be prepared to reach back. The European Space Agency, the Japan Aerospace Exploration Agency, and private institutions began drafting collaboration frameworks for a long-term interstellar monitoring network, a system of wide-field telescopes, automated survey drones, and orbital detectors constantly watching for faint intruders from beyond the sun. Each would carry advanced spectrographs capable of resolving isotopic ratios, plasma densities, and magnetic field strengths in real time. Every encounter would add another page to the growing story of galactic migration. Within this new architecture, 3I Atlas stands as the catalyst. It showed not only that interstellar visitors exist, but that they behave in ways no single instrument can explain. The event exposed the limitations of human perception. Optical telescopes saw light. Radio telescopes heard the hum of charged dust. Infrared arrays felt the faint warmth of energy redistribution. Only by combining them could the true picture emerge, and even then, the picture remained incomplete. Scientists often describe their work as peeling layers from a mystery, but 3I Atlas reversed the metaphor. The more data gathered, the thicker the enigma became, as though each revelation built a new surface around the unknown. Every instrument revealed not answers but new levels of coherence, systems that behaved with intent, yet lacked a source. In the midst of the data flood, a quiet truth crystallized. The instruments themselves were not separate observers but extensions of one collective sense, a planetary nervous system responding to a single pulse of light. Every dish, mirror, and antenna was an organ of perception. Every photon caught was a signal from a cosmic memory. For the scientists who manned these machines, the work took on a strange intimacy. They spoke of the object as though it were alive, describing its moods, its quiet phases, its breathing. They knew these were metaphors, yet they persisted because the behavior warranted them. In the sterile data streams, there was pattern and patience, the hallmarks of order, the qualities humans instinctively associate with life. Through this network of eyes and instruments, humanity glimpsed its own reflection. a civilization building tools not merely to observe, but to feel the rhythms of the universe. The telescopes had become translators between two immensities, human curiosity and cosmic silence. By the third week of October 2025, the monitoring campaign reached its peak. Every major observatory on Earth and in orbit had contributed. The combined dataset spanned wavelengths from radio to ultraviolet, covering the full spectrum of measurable reality. Still, the essence of 3i Atlas, the mechanism of its balance, the cause of its glow, remained hidden beneath the data. No single image captured it whole. No equation held the entirety of its structure. What emerged instead was a composite impression, a metallic heart encased in plasma, a shell that expanded and stabilized, an orbit that ignored disturbance, and a pulse that matched the breathing of the sun. For now, that is enough. Because every new discovery in astronomy begins not with clarity, but with coherence, the faint alignment of mysteries pointing toward a deeper rule. And 3i Atlas, for all its impossibility, radiates that coherence in perfect rhythm. The story of its observation is also the story of our own advancement, of machines built to stretch human vision beyond the horizon of understanding. Each instrument, in its precision and limitation, became a voice in a larger conversation between civilization and cosmos. The dialogue continues in silence, written in wavelengths and stored in data archives that will outlast their observers. Perhaps, decades from now, when the next interstellar wanderer crosses the solar system, the accumulated wisdom of these instruments will be ready, and when its light first touches our detectors, we will no longer ask whether it is comet, asteroid, or anomaly. We will know that every object between the stars carries the same coded truth. That matter, given time and motion, learns how to balance energy and endure. For now, the telescopes remain vigilant, drifting quietly above and around the world, their sensors open to whatever the void decides to send next. In their lenses, 3i Atlas has already become more than a comet. It is a teacher, a reminder that every mystery is also a mirror, and that the universe, when observed with patience, reveals not chaos, but symmetry. When the final observation window closed, the object drifted too far and too faint for direct study. The telescopes turned away. But for scientists on Earth, the work had only begun. Atlas could no longer be touched by light, yet its echo lived inside data. Billions of numbers, waveforms, and spectra preserved across digital archives. In those values, the object still pulsed. In laboratories around the world, researchers tried to rebuild it. They could not reconstruct its size or age, but they could recreate its behavior. The strange stabilization, the organized plasma, the rhythmic brightening that ignored thermodynamics. To understand the phenomenon, they turned simulation into experiment. At the Jet Propulsion Laboratory, engineers filled a magnetic vacuum chamber with iron and silicate dust, imitating the comet's known materials. They rotated magnetic fields around the chamber, sending pulses that mimicked solar wind variations. At first, the dust moved chaotically, turbulent eddies, uncontrolled charge. But after several hours of adjustment, the particles began to form threads. Those threads twisted together into filaments, glowing faintly as they conducted small electrical currents. Within that chamber, for a few seconds, the material aligned into a self-sustaining lattice, a miniature 3i Atlas breathing under artificial sunlight. When the current stopped, it fell apart. But the moment of order proved that nature's design was reproducible, at least in principle. Across the Atlantic, plasma physicists at European research centers used superconducting coils to replicate the electromagnetic environment predicted around 3i Atlas. When they introduced metallic dust into the field, the grains arranged themselves in double layers, alternating positive and negative charge. Under laser illumination, these layers oscillated, releasing bursts of light synchronized with the coil's magnetic frequency. Observers watched in silence. The pattern was too precise to dismiss as random. It looked mathematically and visually like the rhythm seen in the real object's light curve. The phenomenon gained a new name: coherent particulate feedback. It described a system in which microscopic components organize themselves through electromagnetic tension, producing collective stability without a single controlling force. In essence, the matter behaves like a living circuit, responding dynamically to energy flow. Once that term entered discussion, a deeper realization followed. 3I Atlas might not be unique. It might represent a stage in the natural evolution of solid matter, exposed to deep time and interstellar radiation, a phase between inert debris and organized structure. Just as molecules once learned to self-replicate, perhaps dust and metal learned to self-stabilize under the right conditions. Computer simulations supported the idea. When digital models combined metallic conductivity, low gravity, and variable magnetic fields, they produced stable feedback networks that maintained symmetry indefinitely. Energy input from solar radiation produced cyclical expansions and contractions identical to the pulsations observed in 3I Atlas. No intelligence was required, only physics allowed to run its full course. A self-organizing system had emerged from basic laws, the way crystals grow or clouds form, but at a vastly different scale. The implications extended beyond cometary science. If dust clouds in interstellar space can spontaneously organize into energy-efficient systems, they may influence star and planet formation in ways never before modeled. Early simulations of protoplanetary disks were revised to include electromagnetic feedback loops. The results showed faster aggregation, smoother stability, and reduced fragmentation, processes matching the geological uniformity seen in many exoplanetary systems. In this light, 3I Atlas became not an exception, but a fossil record of cosmic construction, a fragment from an era when the laws of physics first experimented with complexity. The concept reached into engineering as well. Material scientists studied how its self-balancing plasma might inspire new technologies: energy harvesters, radiation-resistant alloys, spacecraft shielding capable of redistributing thermal stress. If matter can adapt under solar radiation, then machines could too. The idea that a comet might become a model for artificial resilience blurred the line between discovery and design. By November 2025, international conferences devoted entire sessions to what was now called the Atlas effect, a catch-all term for the unexplained self-stabilization observed during the brightening phase. Papers described it with cautious precision: energy redistribution via field-coupled particulate resonance. No one claimed to understand it, yet no one could deny its consistency. In every attempt to simulate the object's light pattern, the same dynamic emerged: energy flowing inward and outward, reaching equilibrium through resonance rather than dissipation. In theoretical terms, this suggested an alternative form of thermodynamics, one not ruled solely by entropy but by balance. Instead of degrading into randomness, the system seeks a steady state where internal and external forces equalize. It is not perpetual motion, it is perpetual coherence. The laws remain intact, but their expression broadens. Matter under the right conditions may find harmony rather than decay. That realization rippled through the scientific world quietly, without headlines or fanfare. It appeared in equations and revised models, in the tone of lectures where uncertainty became curiosity instead of defeat. Physicists who once described entropy as inevitable began to use new language, words like resilience and feedback and self-tuning. The vocabulary of systems replaced the vocabulary of collapse. Yet in all this progress, the object itself was still gone, moving steadily outward, beyond the reach of telescopes, a point of light fading into interstellar night. Its distance grew each week, but its presence lingered in the hum of simulation chambers and the glow of plasma experiments across the planet. In every laboratory where dust aligned or light pulsed in rhythm, it was as though the universe had lent humanity a small piece of its memory. A sense of reverence spread through the teams who studied it. Not religious, not mystical, just an awareness that they had touched something foundational. For centuries, science had searched for simplicity beneath complexity. Now it was learning that simplicity itself might evolve, adapting to survive change. 3I Atlas had shown that even the smallest structure can echo the persistence of galaxies. The more simulations ran, the more stable the digital models became. Eventually, one model reached near permanence, a virtual particle field that cycled endlessly, converting input energy into balanced motion with zero net loss. In that moment, the term living model gained literal meaning. The simulation behaved as if aware of its boundaries, maintaining equilibrium even when external variables shifted. It responded to changes instead of breaking under them. The behavior was purely mathematical, yet the description felt biological. When researchers presented the results at a closed symposium, they spoke in measured tones. They avoided the word life, but one line in the summary captured what everyone silently felt. We are observing persistence without reproduction, equilibrium without control. It was the closest science could come to awe. By the end of the year, 3I Atlas had passed beyond detection range. Its light, once bright enough to stir global attention, now registered only as noise on the outermost sensors. The world moved on. But in data centers and research labs, the living model continued, an echo of that vanished traveler, sustained by equations and memory. Perhaps in deep space, the original object still pulses in quiet rhythm with the sun that once illuminated it. Perhaps its glow now mirrors another star's magnetic field, repeating the same expansion, the same calm defiance of entropy. If the simulations are correct, it may persist for millions of years, feeding on the balance between radiation and dust, forever adjusting, forever stable. On Earth, the replica pulses too, a machine echoing a cosmic pattern, a human creation repeating a universal act. Between them stretches the same principle that binds galaxies and atoms alike, energy seeking form, and form returning it to energy. Atlas taught that lesson not through words, but through light, through behavior that rewrote what matter can do when left alone long enough to learn itself. Its mystery became a model, its passing a beginning, and though it has vanished beyond reach, the rhythm it left behind continues to guide the minds that study it, proof that even in absence, discovery lives. For months, astronomers spoke of 3I Atlas as an anomaly, a deviation from the rules that hold the universe together. But when the last observation faded and the final graph settled, the anomaly began to look like something else, a reflection. In the glow of that distant traveler, humanity found not a violation of physics but an echo of itself, a symbol of how intelligence behaves in the face of the unknown. Across observatories and laboratories, the response to 3I Atlas mirrored the very phenomenon it inspired. Energy gathered, focused, and transformed into structure. The comet balanced forces of heat and radiation to hold its form. Humans balanced curiosity and humility to hold understanding. Both, in their own way, practiced equilibrium. For centuries, science has pursued meaning through division, separating matter from energy, cause from effect, observer from observed. 3I Atlas blurred those lines. Its behavior made it impossible to distinguish passive from active, natural from adaptive. It was a body that seemed to think without thought, to choose stability without choice. And as researchers tried to define its state, they began to realize that they were also describing themselves. A species that adapts, learns, and seeks balance against the overwhelming forces of entropy. Perhaps that is why the object stirred such fascination. It wasn't just the mystery of its light, but the familiarity of its persistence. It behaved like life, not in biology, but in intent. It absorbed energy, reorganized itself, and survived change. It was the same story that life on Earth tells through every heartbeat and every cell division. In one quiet discussion at a conference, a physicist remarked that 3I Atlas seemed to embody the second law of thermodynamics turned inside out. Not the increase of disorder, but the endurance of order in the face of it. Another replied that perhaps this is not contradiction, but proof that entropy is only half the truth. The universe may indeed tend toward chaos, but along that descent, pockets of symmetry arise. Self-organizing islands of resistance. Stars, planets, living cells, civilizations, and maybe even interstellar debris, all are temporary refusals to yield completely. They exist not because they escape decay, but because they ride its edges with precision. That idea reframed the mystery entirely. Atlas was not a comet that broke the rules. It was a reminder of how flexible the rules are when observed closely enough. Physics at its deepest is not a wall but a dialogue, an agreement between energy and form. The universe doesn't forbid complexity, it invites it, as long as the equations stay balanced. 3I Atlas found that balance in light. Humanity finds it in thought. The parallel runs deeper than metaphor. The object carried within it metals forged in ancient supernovae, nickel and iron atoms born in the heart of dead stars. Those same elements flow in human blood and nerve, Iron binds oxygen in every breath. Nickel strengthens the tools built to study the sky. In a chemical sense, 3I Atlas and its observers were kin. Fragments of stellar memory recognizing each other across the gulf of time. The comet was not visiting strangers. It was returning home to its own material descendants. That recognition carries quiet meaning. If matter can travel from one sun to another, cross billions of years and awaken into light, then the boundaries we imagine, between system and system, life and inanimate, past and present, are illusions of scale. The same atomic narrative continues unbroken. Hydrogen into helium, star into dust, dust into stone, stone into consciousness. 3I Atlas is one verse in that poem and humanity another. Both are instruments through which the universe studies itself. In this light, the questions that filled research papers about luminosity, plasma, feedback, and equilibrium become more than scientific puzzles. They are philosophical mirrors. They ask what it means to endure, to self-correct, to balance chaos with order. And every attempt to answer them reveals the same truth, that curiosity is the human version of that same self-stabilizing process. It is how our species resists entropy, not through mass or magnetism, but through attention. The act of watching, of measuring, of wondering, these are the ways thought maintains coherence in the vast thermal decay of time. As the world moves beyond the event, the scientists who studied 3I Atlas carry subtle changes within them. Some now speak more softly about certainty. Others describe data as dialogue, not conquest. There is a humility that comes from meeting something older than the solar system and realizing it still has lessons to teach. 3I Atlas was a body that seemed to listen to the sun and answer with light. And in studying it, humanity learned to listen to the quiet harmonies between law and exception, prediction and surprise. In that sense, 3I Atlas is not just an object, but an invitation. It asks us to look at our own nature through the lens of equilibrium. The same feedback loops that stabilized its plasma also shape civilizations. Input becomes response, response becomes adaptation. Progress, like orbit, is a form of resonance. Too little energy and it fades. Too much and it collapses. Between them lies the delicate balance where meaning thrives. Einstein once wrote that the most beautiful experience is the mysterious, the source of all true art and science. He might have recognized something of that beauty in 3I Atlas, a phenomenon that returned mystery to the modern age of measurement. For decades, astronomy has pursued precision, shrinking uncertainty with data, but sometimes a discovery widens the horizon instead. It reminds us that knowledge is not the end of wonder. It is its continuation. And so in the faint afterglow of this interstellar visitor, the lesson endures. The universe is not a cold mechanism, but a field of relationships, energy exchanging, balancing, resonating. To study it is to become part of it. Every photon that touched 3I Atlas and then entered a telescope carried not just information, but interaction, a handshake between the cosmos and consciousness. Long after the object has vanished beyond detection, its echo remains, in data archives, in theories still being written, and in the quiet awe that lingers after comprehension ends. It is the same silence that follows music, where understanding gives way to presence. That silence is not empty, it is equilibrium. Perhaps one day another interstellar traveler will arrive and humanity will watch again with steadier instruments and wiser eyes. But even if none come, the lesson is enough. Balance is not an anomaly. It is the universe's most persistent habit, and in the faint rhythmic light of 3I Atlas, we were lucky enough to see that habit expressed. A mirror held up to both cosmos and mind, showing that endurance and understanding are two forms of the same light. By the final days of November 2025, the light of 3I Atlas began to weaken. It did not dim suddenly. It ebbed, like the tide retreating from an unseen shore. The expansion had stopped weeks earlier. The strange anti-tail had narrowed to a thin, silvery thread, and now the entire structure folded back into darkness. Telescopes followed the fading trail until it fell beneath the noise of the stars. For most comets, this moment marks an end. The dissipation of gas, the scattering of dust. But 3I Atlas showed no fragmentation, no violent break. Its brilliance simply relaxed, as if releasing borrowed energy back to the void. The same instruments that had measured its impossible growth now recorded stillness. Luminosity halved, spectra cooling, emissions settling into a quiet continuum. The object remained intact. It neither exploded nor crumbled. It just left. Across observatories, the reaction was oddly subdued. There was no singular announcement, no press conference proclaiming discovery or closure. Instead, researchers archived terabytes of data, cross-referenced readings, and prepared long reports that would take years to interpret. The story that had consumed the world's attention drifted from headlines into databases, from astonishment into documentation. In one sense, this was the normal rhythm of science. Every flare of discovery must eventually fade into the patient analysis that gives it meaning. But this time, the quiet carried weight. Those who had watched the object daily, adjusting instruments, comparing frames, felt the loss like the end of a long conversation. Each new image contained less light than the one before, as though a friend were walking away mid-sentence. Hubble's final composite showed a thin arc trailing behind the nucleus, a memory of the anti-tail dissolving into the solar wind. JWST's infrared sensors caught one last pulse of warmth, then nothing. The coordinates were logged for future surveys, though by the time any telescope returned to them, Atlas would already be billions of kilometers beyond Neptune's orbit. Heading back into the interstellar dark, on Earth, researchers turned inward, comparing notes. The consensus was careful, conservative, but tinged with awe. 3I as Atlas had demonstrated behavior consistent with a self-organizing plasma metallic body responding dynamically to solar radiation as a system that balanced itself under stress and preserved integrity throughout perihelion. No physical model yet explained the internal mechanism, but none denied the data. It had happened. And that fact alone was revolutionary. Months from now, papers will appear, conferences will convene, arguments will sharpen around interpretation. Some will insist that all anomalies can eventually be reconciled with conventional physics. Others will argue that a new framework is required, one that includes feedback as a natural force, not an exception. But beneath those debates will lie a shared memory. The experience of watching an object from another star defy collapse and simply remain whole. For the broader world, the fascination faded quickly. New discoveries claimed attention. New mysteries arrived to replace the old. But for the scientists who had watched it, the event left a permanent mark. Every comet, every asteroid, every glow in the sky afterward seemed slightly more alive. Every data set more fragile. Every explanation provisional. There is a moment in every investigation when the unknown stops resisting and begins to recede. Not solved, not conquered, just distant. That was how 3I Atlas ended. Not with revelation, but with perspective. It had shown the universe holding a mirror to its observers. And when the reflection dimmed, what remained was gratitude. The last telemetry line closed on December 2nd, 2025. One final reading of reflected sunlight returned a value near zero. After that, the object vanished from measurable space. Yet its presence endures in another form. In every model recalibrated, every sensor upgraded, every young scientist drawn to astronomy by the thought that somewhere beyond the edge of our star's influence, a traveler once grew brighter for reasons still unknown. In cosmic terms, its visit lasted an instant, a single heartbeat in the life of the galaxy. But that instant was enough. Because light once seen never truly disappears. It only travels farther than eyes can follow. And long after 3I Atlas fades into the interstellar dark, its photons continue outward, carrying the memory of their impossible source into the endless night. Space does not remember names, only patterns. The path of 3I Atlas will dissolve into the starfield like ink into water, its trail erased by time and motion, but its echo remains, a template of possibility now written into the sky. For every known comet that circles the sun, there are countless others that never will. Silent wanderers crossing the gulf between stars. Some are shards of planets torn apart by gravity. Others, unburned embers of creation, drift cold through the dark until a chance encounter wakes them into light. 3I Atlas was one of these, and somewhere another waits. Astronomers know this not by faith but by mathematics. Statistical modeling based on the last decade's surveys predicts that several interstellar objects pass through the solar system every few years. Most too small, too faint, or too fast to notice. The improved sensitivity of new instruments means that the next one may already be on its way, crossing the outer edges of the Kuiper Belt unseen, carrying with it another set of impossible answers. When it arrives, the world will be ready in a way it wasn't before. Plans already exist. The Interstellar Object Observatory Network, a collaboration between NASA, ESA, and multiple research institutions, will begin operation in 2026. Its wide-field telescopes, stationed at different points around the globe, will watch the sky continuously, feeding real-time data into a unified detection system. Artificial intelligence will sift through millions of moving points of light each night, identifying the telltale hyperbolic trajectories that betray an origin beyond the sun. Once detected, an automated alert will trigger orbital telescopes and, if timing allows, launch windows for intercept missions, a choreography of readiness born directly from the lessons of 3I Atlas. This is the legacy of the luminous wanderer, preparation. It taught the world that the universe still sends messages, and that the greatest risk is not mystery but delay. By the time Oumuamua was identified, it was already leaving. By the time Borisov was studied, it was fragmenting. By the time 3I Atlas brightened, it was too far to reach. The next one might come sooner, slower, or closer. And this time, the instruments will not just watch. They will move. Among the most ambitious designs is Project Lyra, a fleet of small, high-acceleration probes meant to intercept interstellar bodies within months of discovery. Each will carry microspectrometers, plasma sensors, and onboard AI for autonomous navigation. They will not return samples. They will become the samples, transmitting their data back before they vanish into the dark. Every probe is a question launched into infinity, trusting that some answers can only be found by joining the mystery itself. As this new era of exploration unfolds, a quiet realization takes root among the scientists who watch the stars. Perhaps these objects are not random visitors, but participants in a larger exchange. Every star births material that someday leaves its grasp, carrying within it the chemical signature of its origin. When those fragments cross new systems, they share their inheritance, scattering the ingredients for worlds and occasionally for thought. The galaxy, then, is not a collection of isolated systems, but a single organism exchanging matter across billions of years. Each interstellar traveler is a pulse in that circulatory system, and 3I Atlas, in its strange glow and impossible calm, was simply a heartbeat that happened to pass close enough to see. For those who watched it, the silence after its passing feels temporary. Every data stream that once measured its light now listens for a new signal. Every formula refined to explain it now waits for new variables. And every young mind inspired by its story begins another cycle of curiosity, a feedback loop of its own. The object may be gone, but the rhythm it awakened continues. Observation leading to wonder, wonder leading to pursuit, pursuit leading back to mystery. Somewhere beyond the heliopause, 3I Atlas continues its journey through interstellar space, glowing faintly in wavelengths too weak for any human eye. Perhaps one distant day it will pass near another star, warming again, pulsing again, resuming the slow conversation between light and gravity that never truly ends. In that moment, on some other world orbiting some other sun, another civilization might see what we saw, a small, inexplicable brightness, and the realization that they, too, are not alone in their curiosity. In that possibility lies comfort. The cosmos is vast, silent, and ancient, yet not indifferent. It allows patterns to repeat. It lets questions echo. And through those echoes, intelligence recognizes itself, scattered across time, connected by light. Atlas has left the solar system, but the mystery remains, not as absence, but as direction. Because every unanswered question points somewhere, and somewhere, beyond the edge of sight, another traveler is already coming.
Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video.